Okay. All good? Okay.
Okay. Is this on?
Let's see. Maybe we need to hit the, yeah, it needs to be. There you go.
Okay, awesome.
Awesome. Please, take it away.
Thank you. Okay, awesome. So I'm Manya, and today I'm going to be talking about our work that enables you to write low-level and modular programs for the GPU. Before I start, I want to give a quick refresher on GPUs. So on a GPU, execution happens thousands of threads at a time. It's a massively parallel architecture. And the most popular way to program GPUs is to use CUDA. In CUDA, you control the machine by defining the behavior of a single thread. So let's see what this actually means in practice. We're going to multiply a matrix, again, multiply A and B, compute output into C. And the way that we're going to do it is we're going to read the global thread ID, more about how we're going to compute this later. And this is going to be different across all of the threads. Using this different value, we will basically write something that looks like a parallel for loop, if you've seen it in other programming paradigms. And using that, we can actually distribute the entire computation. Now, internally, the GPU is actually organized in a hierarchy. So there's a single thread, which is the smallest unit of sequential control. There's a warp, which is a group of 32 threads. Instructions are issued 32 threads at a time, and they execute in lockstep. A block contains a configurable number of warps, a grid, a configurable number of blocks. And this hierarchy is not only useful to logically organize your computation, but rather has meaning. Certain operations are only meaningful when executed at certain parts of the hierarchy. So an example of this is the Tensor Core operation. On the Ampere generation, a warp level of the hierarchy is the level of the hierarchy where you can go and execute this operation. And this is where most of our compute lives. So we really care about this. Let's see how we can program this in CUDA now. Like before, we have a function. Each thread is going to be executing its own copy of the function. It's going to locate itself by reading an ID. After doing that, because we're now going to execute a warp level operation, 32 threads, we're going to have this if statement, read the inputs to this operation, perform the actual operation, then finally write the outputs, and then synchronize all threads in the warp to make sure every thread has basically gotten to that point. The thing I want to highlight is that if I had made a minor mistake, so instead of 32 threads, I had written 31 threads, well then this Tensor Core operation would have actually been undefined. Worse still, that sync warp would have actually deadlocked our entire machine. It's going to wait for 32 threads or a warp's worth of thread to get there. That's not going to happen, so we're just going to hang. And this is actually kind of OK. At least it's in the same function implementation. But actually, this can totally happen in the context in which you can invoke that function. So if the outer context doesn't realize that the inner function is going to try and perform this collective operation, you're stuck. So basically, all is well and good in CUDA until you're actually doing writing programs that are data parallel over threads. And all hell breaks loose when threads need to collaborate. And the situation is a little bit worse still, because I showed you two functions. I showed you a warp function, and I showed you a grid function. And they need to be called differently in different contexts. The issue is, looking at their interfaces, I actually cannot tell this difference. And so modularity fundamentally is broken in the CUDA programming model. In fact, I want to argue that the ecosystem reflects this lack of modularity. Many libraries, like the ones on the screen, can only allow you to control the entire machine at once. So they can't even be composed with anything else. But those libraries, like Cub, that actually do try to introduce finer-grained interfaces, actually expose that assumption in their names. And this should really send a shiver down everybody's spine here, because names are just names. They can't be checked or enforced. And you may be wondering, well, Manya, I've heard about the N million GPU languages. What about any of those? Let's take Triton as an example, which is a block-level programming language. In Cub, we at least have 3 options. In Triton, we only have 1. So we actually don't need to make a choice, because we don't have any. And this is great until you actually want to perform a warp group level tensor core operation. Well, in this case, you would want my presentation to keep presenting. Let's see.
It's a very dramatic surprise.
Yeah, it's a dramatic problem. Yeah, in that case, literally all does go dark, in that you basically rely on the compiler to figure out what's going on. So actually, Triton has introduced this lower-level programming model called gluon, and then basically, gluon is the thing that we need to use to program this machine now. So you may be wondering then, well, Manya, I can see you're going to propose a language. What level of the hierarchy are you planning on choosing? And I think this is a general question that current GPU programming languages ask of themselves. At what abstraction should they expose the machine so that they can still continue sort of providing modularity without sacrificing performance? And I think this is the wrong question to ask. In this talk, I want to propose a different question. I want to ask, how do we give access to the lowest level interfaces on this machine without sacrificing modularity? And I answer this question by proposing a language called Prism. So Prism is a low-level GPU language that tracks in its type system how code is going to be using hardware resources. Using this tracking, it checks at function invocation time that the function is only being called if those hardware resources are actually available. The core idea at the heart of Prism is this idea of a perspective. A perspective is simply the view of the hierarchy from which we're going to be defining the machine's behavior. Let's see what this actually means. So in our simple tensor core example, we could actually already see perspectives in play. So that first statement there is a thread perspective statement. Literally every thread even has different values for that x variable. The next if statement, a warp perspective. The next two register-based loads are thread perspective. The tensor core, of course, requires the entire warp, a warp perspective statement. Same for those threads. And then finally, the sync warp, also a collective operation from the perspective of a warp. Given this intuition, let's operationalize our definition of a perspective. So a perspective is simply a level, a grid, a block, or a thread, coupled with a static constant. So a thread 1 perspective is simply a single thread. A thread 32 perspective is a perspective that contains 32 threads. A grid 1 perspective is single grid. In Prism, perspectives are aligned by default. No worries if you don't know what that is about GPU programming, but for all the experts in the room, that means thread 32 perspective is always aligned and therefore always maps to a warp. So if we go back to the original program now, we can annotate with this program with the perspectives through a thread 1 perspective statement, the thread 32 perspective if statement, thread 1 loads, thread 32 tensor core invocation, thread 1 stores, and thread 32 sync warp. Now the question that is sort of really important for us to answer is that how do we actually ensure that the perspectives we've actually annotated in the program are respected? And for this, Prism basically exposes them in the program source. So let's actually take this program and try to rewrite it in Prism. The first thing we have to deal with is that if statement, because depending on that if statement, our collective operations are going to be valid or invalid. The first construct then that I want to introduce is this construct of a split. A split statement basically helps you shard your compute resources into different parallel pieces. So each arm of that split is going to execute in parallel, and then that tensor core operation is valid because it lies in that scope of that thread 32 split. Now, this is not the only way you might want to shard your compute resources. So we have another construct called group, which basically takes a perspective and replicates its body across that perspective. So in this way, it kind of forks off multiple copies of that perspective executing that same code. Now, group and split attempt to make a certain promise to their programmers. They say, in our scope, the compute resources are going to remain logically coherent. So in that scope, there's always going to be 32 threads executing that computation. Actually, as it stands, I can make it so that this is not true. So if I just look at that x variable that contains different values and just simply branch using that value, well, then the tensor core operation is in trouble. That's going to be undefined behavior now. And in general, this is going to be a problem for us, because you can use divergence on data to induce divergence on compute. And the way we solve this on Prism is that we actually track divergence on data so that it cannot induce untracked divergence on compute. So only groups and splits can induce divergence on compute. Let me show you what this means. So if we go back now to our original example, well, that data x simply lives at another perspective. That's a thread 1 perspective variable, which is to say it changes at the frequency of thread 1. Now, if I had instead tried to branch on the value of the thread 1, that's a compile time error. My compiler is going to scream at me because I actually cannot read that data. Let's dig a little bit deeper into the rules for reading and writing into data in Prism. So if I had a variable x here, like the thread 1 perspective variable, changes at the frequency of thread 1. And if I had another variable y, which changes at the frequency of thread 2, so it changes at most at the frequency of thread 2, then is it OK if I try to write the value of y into x? Well, let's try doing that. And this turns out is actually totally OK, because that x variable continues to meet its contract of changing at frequency thread 1. It's just a contract that sets sort of the upper bound on how often it can change. So this is totally fine. However, if I just sort of reset this operation now, and then try to write the value of x into y, well, then I'm in trouble. I've actually violated the contract that y sets up for itself. In general, data can read from broader perspectives, but broader perspectives cannot write into narrower perspectives. With this in mind, we can continue converting the other data into our program into this perspective form. So x now is a variable that lives at thread 1 perspective. We can also change our registers. And we can also change the actual function interface a little bit. Now, I do want to point out that that's a memory operation. And so we'll talk about this a little bit. But just to understand what that actually at thread 32 is doing, it's just saying that the value of that pointer for each of those threads in the group of 32 threads is exactly the same. It says they're sort of converged on that value currently. Now, since I allow reading from broader perspectives, I can simply now convert that read from the broader perspective into the narrow perspective, but I still somehow need to handle writing into that memory. Well, for that, we have another construct called partition. Partition basically takes in memory that lives at a broader perspective, lowers it to a smaller perspective, so that thread 1 perspective, and in doing so, basically takes a function that helps us do this and introduces a new name. So cthread value is now going to be different for the body of that partition based on the function that we actually give it. So every time you index into cthread now, it's going to automatically be indexed off of that function. Again, you might have noticed I've actually not fully grappled with the true memory hierarchy on the GPU. I've not talked about shared memory, global memory, and so on. Basically, this is like a can of worms that we do completely handle in the paper, so I would recommend reading it. In fact, a lot of people who presented right before me have awesome work handling this. So for more details on memory, you should read the paper, but it's basically almost a direct analog on how we handle compute. Last piece is now the core piece is how do we actually call these collective functions. So turns out every function in Prism carries a requirement with it. And we check the body of each function against that requirement. So now when we actually want to call this collective operation, there's simple function calls. And we can actually check the fact that we meet the requirements because their interfaces tell us what the requirements are. And in this way, we get modularity. We also implement some pretty popular intrinsics within the compiler itself, so user code doesn't need to add it, but you can very well do that. Now, everything that I've talked about in Prism has been formalized in this core calculus that statically tracks perspective on code and data. A lot of ideas in this calculus are borrowed from dependency tracking. So we basically use dependency tracking to make claims about how data from broader perspective cannot flow into data located at a narrower perspective. Using this, we prove a soundness theorem that says that programmers can never execute operations for which they lack the correct perspective. Again, more details in the paper. Finally, we test whether Prism can actually perform speed of light computations. To do this, first we implement the single pass prefix scan algorithm with decoupled lookback Here's a really scary picture to intimidate everybody. No need to understand this, but the upshot here is that the convergence and divergence that you see in this picture is actually fundamentally different from the ones in like dense tensor programming. So basically, Prism can express a lot of variance, and we can match speed of light performance against existing libraries. Again, we also implement the quintessential matrix multiplication example as in asynchronous, pipelined, warp-specialized, calling into Tensor Core for the H100, and we benchmark against the cuBLAS library. There's a 10% difference, not because Prism can't express something, but rather a compiler pass that triggers in cuBLAS does not actually trigger in Prism. Ask me a question if you're interested. But hopefully at this point, I've convinced you that Prism is a low-level modular GPU programming language, and I'm happy to answer any questions that you might have.
Thanks for the talk and sharing your perspective.
Thank you.
Go ahead and take the first question.
Thank you, Hank from UIUC. I have a question that there are, in modern GPU programming, there are certain cases that asynchronous tasks are for the entire block or the warp is initiated by one single thread.
Yes.
How can Prism check and model and check that?
Yes.
Thanks.
So Prism does totally handle it. But I want to also be clear. So the kind of memory guarantees that we actually provide in Prism are not data race freedom or anything like that. Actually, in Prism, we allow bounded data races. And there's a lot of detail in the paper. But the H100 example that I showed you took advantage of TMA loads and stores to actually do warp specialization and load up data. Otherwise, it's like impossible to get the kind of performance that we got. But the way that it works is that similar to Split, where we have sort of a sharding of resources on compute, we have an operation called claim that helps you sort of shard a piece of memory across two competing, like compute resources. And using that operation, we can prove a bunch of things about asynchronous data movement. Yeah.
Thank you.
Do we have any other questions? Okay, I'm going to take one from someone who can't ask her at the lab later. Sorry, David.
Just a quick, simple question. Gaxiang from Columbia University. So, do you prove the semantic, the functional of semantic equivalence between your Prism code to the lower level CUDA, or not?
I mean, so the thing that we prove is that the type system, it's like the normal like syntax operational semantics equivalence. The operational semantics that we model, we don't. We do so with like a good faith model of the actual machine. But the actual operational semantics that we claim, we assume that they are faithfully modeling the machine.
If we have a third question, we can take it. I'll take it in the back here while we're changing over. Pardon. Give me a second, Shri.
Hi. Shripati Pai from the University of Rochester. So this has been a problem since CUDA 1, so this is a really nice approach. I still don't think that a programmer should decide how work is divided among the warps and threads. So do you plan to do some sort of inference, like you're calling this from this perspective, so as to choose between these functions that have been provided by the programmer or something like that?
So this is a really good question, and I think this goes to something like I believe at my core, at least currently, which is that to actually write speed of light performant GPU code, you need to give programmers ultimate control. And let me give you an example of a scenario where this is actually necessary. So in the hopper, the way that you actually write a speed of light warp specialized matrix multiplication is that in your producer warps, you at like runtime dynamically give up registers. This is like an absurd thing to do, and any compiler writer would like, this is like a crazy thing from the perspective of a compiler writer. So I don't think at least GPU architecture stabilize enough that we know all of these tricks, which I don't know. I think oftentimes even for CPUs, we're handwriting code, but certainly for GPUs, architectures as they stand today, it's kind of impossible to for a compiler or like an automatic machine to come up with all these tricks without having seen it in the first place. So yeah.
Okay, I completely disagree with you, but I have one.
Let's definitely argue about this. Yeah.
Well, sounds like a wonderful argument to have in the break, but for now we have a